chair conformations of cyclohexanes. We had just completed the Newman projections section, so let's do a little review of Newman projections. Okay, start question. So the first one, hopefully relatively straightforward. Which of the following are staggered conformations? Anybody waiting in the room? Oh, here. Oops. Alrighty, let's see how everybody did here. Responses. A and C of the majority, right? So anytime there is, where's a little laser? Okay. Anytime there is a so eclipsing conformations, the two bonds are basically lined up with one another. So the eclipsing conformations bonds are basically overlapping, and staggered conformations, there is, I guess this would be 60 degrees between each, approximately between each bond. I'll admit someone to the room. So right, so A and C will be the correct staggered conformations. All right, let's go to the next one. Now there are special names for some of these conformations here. What is the name associated with this one? I have about 10 seconds left. All righty. Here, responses, anti. So the majority have said anti, right. So this is a special form of eclipse of staggered conformation where the two large groups are on opposite sides from each other. So this is anti-conformation. What we're going to see later on is that in the elimination reaction section that certain reactions can only take place if the group which is being eliminated, if the two components are anti to one another. So they have to be basically 180 degrees from across the bond. Okay, good. Next slide. Correct responses was anti. Now, there's another staggered conformation which has a special name. Couple seconds left. Alrighty. So this is a staggered conformation, and the response is gauche. Yes, that is correct. So when the two groups are close by, 60 degrees from each other, this is considered a gauche conformation, and there's a certain amount of energy based upon the interaction of two groups which take up space getting too close to one another. So this conformation's energy is higher than the one which is anti, with this type of energy strain, I should say, doesn't exist. Okay, so we'll get to that in a second. And here we go. What was the name for the type of strain associated with the Gauss conformer? Is it torsional strain, ring strain, steric strain? Is it a combination of torsional and steric, or is there none? Okay, that's good. Alrighty, here we go. Responses. Steric is the most popular answer. Steric and torsional. Okay, so there's two types of strain we learned about yesterday. Torsional strain is the strain of in an eclipsing conformation when the energy of the two bonds is basically the electrons within two bonds is repulsive, so repulsive sort of energy. Steric strain is when you put two fragments or atoms too close together and they both are taking up space. So they're getting too close to one another, and we call that steric strain. So in the Gauss conformation, the electrons aren't lined up. It's a staggered conformation, so you don't have to really worry about the electrons repulsing one another in the sigma bonds here. But remember, a methyl group is tetrahedral. It's got little protons pointing off of it. And when they get together, get too close together, there's a repulsive sort of force that you're forcing groups that are big too close to one another. So it is in fact a steric type of strain. So with staggered conformations, the main type of strain will be steric, where you get large groups, which will be in the Gauss conformation to each other. With eclipsing conformers, you can have a combination of steric and torsional strain. Okay, and I think that leads us into the next question. So I've got 4 conformations of the same molecule, and what we're doing is we're ranking them from lowest energy to highest energy. So first will be the lowest energy, and highest will be fourth, I guess. So the way to approach this is to look at each molecule and think of what potential strain there is, and then the one which has got the least, put that first, and basically work your way down that way. Add a couple seconds to this. Okay, almost done. Okay, so as a basic rule of thumb, staggered conformations will be lower in energy than eclipsing conformations. So the choice between first and second should be between A and C, and the choice for between third and fourth should be between B and D. Because eclipsing conformations have got torsional strain. It's a basic minimum. They're going to have torsional strain, but they could also have steric strain if you've got two large groups eclipsing one another. Whereas in staggered conformations, the only energy you're going to have would be steric strain, so that would only take place in a gauche type conformation. So what did everybody put here? Conformer A being the lowest and conformer D being the highest, with B being third and C being second. Those are the most popular answers. Obviously, these two are mixed up a bit with regard to 31 for highest and lowest. Okay, so that is in fact going to be correct. So if we're doing analysis between A and C for the lowest energy, in A, we've got a methyl group and the ethyl group are gauche to one another. In conformer C, we've got one gauche interaction, two gauche interactions. So this one should be higher in energy than A, which would make A the lowest energy. So that is correct. A first, C second, and then when it comes between B and D, the highest energy conformation here. So in B, we've got an ethyl group, methyl group, and methyl group. They're all eclipsing little hydrogens. So there'll be certainly torsional strain in all of three of these, for all three of these bonds here. What D has got going against it is that we'll have some torsional strain between H and H. We'll have torsional strain between H and M, or methyl, sorry. But the methyl and the ethyl, the torsional strain here, but we've got these two large groups. So the steric strain is gonna be quite high here. So the D should be the lowest. So that is correct. So this basic order was correct. B, then C, A, and then finally D. Good. All right. Okay, last question. This one is all about Newman projections and perspective. So I've drawn a, we call these things sawhorse, like a sawhorse type of thing. I don't know what the, anyway, if we're looking at it down this bond, here's your eyeball, and these are supposed to be your eyelashes, so this is up. Which of these Newman projections is the correct one if you're looking at this from this perspective? Add a bit more time. Let's see. E is the most popular, followed by C. There's a little bit of everything here. Okay, so how do we tackle this? So when we're drawing a Newman projection, and we're looking at it in this direction, so this carbon here is going to be the little dot, basically the dot, the front of all of these, for which these three bonds are taken, pointed away from. The back carbon here is the large circle. So the back carbon is the circle. And if we are looking at this from this perspective, so we're looking down this bond, you will notice that there is one group that is basically pointing straight down from our perspective, like straight down. And that group is a methyl group. So on this little dot here, there should be a line pointing straight down for if you want to have looking at it from this perspective. So this one we have a line pointing up, so it won't be A because this is in the opposite direction. On conformer B, we've got something pointing straight down, but in this case it's an H. It's not a methyl group, so it should be a CH3, so it can't be B. C here, we've got a group pointing straight down, and that is a methyl group, so it could be C. In D, the methyl group's pointing straight up, so it won't be D. And in number E, of course, there is a methyl group pointing straight down. So from what we got right now, it should be either C or E. These would be the two possibilities. Now, the next step is to make sure that you can tackle this a couple other ways. You can what I would typically do is look at the front carbon first and see what's attached to the front carbon. So when we're looking at this through this perspective, all of the dashed lines which are going into the board, so this chlorine or this methyl group, they are on our left-hand side because with our eyeball we are looking this direction. So if you were to turn yourself so you're looking at the far wall, like, and this is the plane of the board where your eye is. Everything on your left-hand side is into the wall, and everything on your right-hand side is pointing further away. So the wedges are on the right-hand side. So this H and this iodine are on the right-hand side. So what we have on our left-hand side is a chlorine. So in conformer C, on the left-hand side is a chlorine. Okay, good. And our right-hand side is a proton. Perfect. The same thing in E. So both of these have got the same conformation on the front carbon. So we haven't decided anything yet. We'll have to look at the back carbon next. So on the back carbon, we've got an H pointing straight up, H pointing straight up, H pointing straight up. So they're both good. Going into the board, or on our left-hand side, is a methyl group. So on conformer C, on our left-hand side, is an iodine. So that isn't good. It should be a methyl group. In conformer E, on the left-hand side is the methyl group, and on the right-hand side is the iodide. So E is the correct conformation. C, this one, we've got these two groups mixed up. So these would be, when we get into the next section, these would actually be what we would call stereoisomers. So methyl group on the left-hand side. So the correct response is E. Almost C, but not quite. So that is good. A couple of these have been drawn. For example, A is actually the correct conformer if you were looking at it from this direction over here. If you were looking this way, A would be the correct one. So, because you would have a proton pointing straight up on the front carbon, methyl on the right-hand side, proton up, methyl on the right-hand side, iodide on the left. Methyl straight down, chlorine on the right, H on the left. So if we're looking at it from this direction. So A would be the conformation if you're looking at it from this direction. Anyway, so that's good. Any questions on any of those? All right, hearing none, we'll go into where we left off last class. So where we left off last class was that we were talking about cyclohexanes and that they were not flat species. Unlike an aromatic ring, which is all sp2 hybridized, cyclohexanes are sp3 hybridized, so each carbon is a tetrahedral. And so we introduced this concept of a chair conformation, and here is our chair. So these two carbons, which are sort of drawn in bold, they're closer to us, and these two carbons in the back, they're further away. So we're looking at this from the side. And I made a little chair that here, which basically depicts, like, for you guys, these two carbons would be closer, which would represent these two here, whereas these two carbons are closer to me, but further away from you if you're looking through the camera. So it looks like a lounge chair, and that's where it gets its name from. And because each four of these, all of the carbons, all six of the carbons are tetrahedral, there's no strain really associated with any of these carbons. And cyclohexanes, like cyclopentanes, are quite common in nature because the carbons can adopt their natural sort of tetrahedral type geometry. So now, when you have a chair conformation, there's actually two different types of protons associated with the chair. The first set we'd call axial, which are in green, and there's three pointing straight up, 1, 2, 3. So they're all on bonds pointing straight up, all on carbons that are peaks, as I would say, because they're higher than the other three. And then the ones which are on the valleys at the bottom, the axial protons are pointing straight down. And then we've got 6 protons that ring the equator, and we call these equatorial protons. So this is basically the chair conformation. And what we need to do is be able to draw these things. And so, yeah, there's a little process. Did everyone practice drawing a chair? I take it from the silence that no one did. Let's see here. Well.
Yeah, no, I didn't.
Okay, well, what we're gonna do next is practice how to draw these things. Okay, so there's basically, right, let's do the whole thing first. Okay, let's see here. I'm gonna draw with this guy. So there's basically there's a couple of steps here. The first step is you can draw, what we're gonna see is there's 2 types of chairs that you can draw. Erase this. The key point is to have, at the start, 2 parallel lines that are slightly offset. And you can draw them in either direction. And in doing so, what we're going to end up doing is making 2 different types of chairs. But the key point is this line and this line should be, the 2 lines should be hopefully parallel. Then you can, in this chair here, we'll draw a point facing down. So, and a way to check this is once you've done this part, if this is a low carbon, you should have 2 peaks, 1, 2. So over here, this would be the high end. And so we want a carbon pointing straight down. So it'd be like there and there. I can tell right away that this chair on the right is going to be a bit ugly, but that's okay. Okay, then you're going to draw a point facing up. And note the 2 lines you draw should be parallel in step 2. So if we draw this going up here, hopefully this line and this line should be parallel, and this line here in bold and this line here should be parallel, hopefully. So this line and this line should be parallel, and this line and this line should be parallel. So that gives you your 2 chairs. Now, as time goes on, you might get good enough to be able to just draw things freehand. And there is, there is, you can come up with some pretty brutal looking chairs doing it freehand, even with lots of experience like I just did. So, but anyway, so typical 2 parallel lines, draw a point down, point up, and then hopefully all of your lines tend to be parallel. So we've drawn all the carbons on here. Now, what we're going to need to be able to do next is be able to draw the protons. And so let's go to the next slide here. Stop drawing. I guess I better stop. I'm gonna sneeze. Now we need to be able to draw the protons. Oh, they moved over. Okay, good. So drawing the axial protons is easy compared to the other ones. Let's see, drawing the axial protons is easy because sorry about that. Drawing axial protons is easy because on our carbon, we're going to have 3 carbons that are peaks that are like going up, like a peak, 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 and we're going to have 3 carbons that are valleys. So this going down, this is a valley carbon, this going down, this is a valley carbon, and likewise. So I guess I should use my laser for that. So like peak, up, like a peak, up. So this is up, up, peak, up, that's up. And then the valleys down, down, and down. So the axial protons, all you need to do is if it's a peak up, you just draw a line straight up. H, up, up. And if it's a valley, like just a line straight down. So those ones are the easy ones to draw. Peak up, you just draw a straight line up. Valley, just draw a line straight down. Now, the equatorial protons, however, I'm going to draw another chair over here. They are a bit more difficult to see at the start. But what we're going to do is we are going to use the concept of parallel lines again. So on this drawing over here on the right, so every carbon should be tetrahedral. So if we're looking at this carbon on the, which I'm sort of making this dot bigger, if you notice there's a bond, 1 bond here, 2 bonds here, 3 bonds here. It's missing a bond, and it should be a tetrahedron. So the direction where this proton is missing from is somewhere over here on the right. And so we need to put a proton there. And so it should be parallel, this proton here should be parallel with these 2 lines. So this line, it should be, that proton should be parallel to those 2 lines. And on the other end of the cyclohexane, this proton over here should be parallel to the same 2 lines. So the body of your tetrahedron, which I'm going to bold out over here, the 2 protons which should be parallel to that are the ones on the end. So this red line here will be parallel to the ones in the middle. The other, so those 2 are the easiest equatorial protons to draw. The other ones are a bit more difficult. So the protons here and here are going to be parallel, like this one here is going to be parallel to that line. So, and it's going to be pointing down because we've already got an axial proton pointing up. So this bond here should be parallel to that line. And this proton over here should be parallel to this line. So parallel, parallel. And then the 2 protons on the back, these are both going to be pointing away from us. They are going to be parallel to the 2 lines that we haven't bolded yet. So this proton here will be parallel to this line, and this proton here will be parallel to that line. So all of the equatorial protons are parallel to bonds within the cyclohexane. So that's what this little part at the bottom here is trying to depict, is how to draw which lines these protons should be. So, but of all of these equatorial protons, the 2 which are kind of pointing towards us would be this one and this one. The 2 that are in the plane of the board would be the ones in the squares here. And the ones that are farthest away from us, which are pointing away, would be the ones in the clouds, these 2 at the back. So that's sort of how that works. So we sort of think of this as that the plane of the blackboard bisects the carbons at the 2 ends of the chair. The bond here is closer to us and the bond back here is further away. So that's basically how all of that works. So what we need to do is get some practice drawing chairs. Usually what I do for that is I sip on my coffee and I have everyone draw some chairs and show them to me. Now, how are we going to do that today? There's actually a way we can do that. And so what I'll do is I'm going to, and one of the great joys of drawing chairs is being able to show your chair to your fellow classmates. What I'm going to do is I'm going to break everybody out into like 10 rooms or something. And the 4 or 3 of you who are stuck in those rooms can draw some chairs and then share them with your friends. And you can, and then everyone will be able to see that everyone is capable of drawing a chair. And then after that, what we'll do is we're going to talk about what happens when we put substituents or alkyl groups or hydroxyl groups on these cyclohexanes. So let's see here. How do I do that? Okay, so what I'm going to do is this is completely random. You're going to meet some of your classmates in the next couple seconds. I've basically made 10 rooms. Everyone can enter your room, draw your cyclohexane, and then basically use your cameras to share them with your soon-to-be friends. So what you can do is basically, yeah, try to draw your chairs, and then once you've got a nice looking chair, share it with everybody. And then I'll come back and check on everyone. I guess I can stop the recording. I think I have to change my virtual background outside of the actual meeting, so I can't do it right now. But in the conformational change, like this carbon here, the white balls are actually axial protons. And when it undergoes a conformational change, this what we call chair flip, all of the axial protons then become, instead of being white, are now green. So the act of moving this carbon up and this carbon down, it actually changes, or this one coming down and this one going up, it interconverts these two chairs. We call this a ring flip. And so in the course of a ring flip, everything that was axial becomes equatorial, and everything which was equatorial becomes axial. That's basically what's going on. It's not turning the molecule over, because if you turn the molecule over, everything which is axial is still axial. It's just pointing in the opposite direction. So a chair flip actually involves things that were once axial then become equatorial. So I think on the next slide, I've tried to describe this. Yes, with the little balls. So we've got our pointy end here down on the left, and we've got our pointy end up on the left on the other chair conformation. And so in the process of this going up, it changes from being equatorial to axial, and the red axial group becomes equatorial. So, and this takes place on every single carbon. So everything that you notice on the chair conformation on the left, all of the axial, all the equatorial groups are green, and on the right, all the equatorial groups are red. So if you've got a model at home, you can make a chair, and then you can label, once you've made your chair, you can put all of the axial groups one color, and all the equatorial groups another color. And then if you go through the process of doing the actual chair flip, the two groups should change location. They should go from being equatorial to axial or vice versa. Yeah, so that's basically, so these chairs they're conformationally mobile. So you can actually move a group up, move a group down, and in the process it changes things from being what was axial becomes equatorial, what was equatorial becomes axial. Now, why is this important? This is important when you've got substituents on your ring system. So here we've got basically, this is methyl cyclohexane. So we've got a methyl group on cyclohexane. And when you have a bottle of this on the shelf, if you're to do an analysis of it at room temperature, you would find that 95% of the molecules in that bottle have an equatorial methyl group, whereas the remaining 5% have an axial methyl group. And so, yeah, and this is an equilibrium. So it's undergoing this chair flip, but at any given time, 95% is equatorial, 5% is axial. So with regard to the equilibrium arrows here, I've basically drawn this arrow pointed mainly in one direction. So what this is actually telling us is that these two conformations or conformers are not equally stable. The equatorial one is stable by 7.6 kilojoules per mole. So the number really isn't important. What we're going to do is we're going to put a variety of groups on a cyclohexane, and we're going to be able to do an analysis and tell which one should be the more stable conformer, and that's really what we're looking for here. So why is this group in the equatorial position more stable than this group in the axial position? The answer to this basically lies with the Gauss conformation of butane when we did that. So there is a strain associated with cyclohexanes, and it's called 1,3-diaxial strain. And so whenever you've got a methyl group in an axial position, there is a strain associated with the protons in the other axial position. So that's why it's like the 1,3-diaxial. So this methyl group, it's got interaction with this proton and this proton. Whereas when the group is in an equatorial conformation, there is no diaxial interaction. So that's basically, there's no, and this interaction here is essentially a Gauss interaction. And to see this, we really have to draw this as two Newman projections, or a Newman projection, or just a very complex Newman projection. So that's what I've tried to draw here. So if we've got a methyl group, and then it's a staggered conformation, next door is a methyl group, you'll see that what I've done here is I've drawn this carbon, and I've actually put the protons on it, right? And there's a proton here. So this is a Gauss interaction. And so if we draw a cyclohexane and we're looking down the two bonds, this is basically what the cyclohexane would look like. Here's your methyl group, and there's a Gauss interaction with this carbon here, but it's really this proton. And then if we draw this in a different perspective, this proton would also have this same this Gauss interaction here. So the moral of the story is that anytime you've got an axial group, it can have a 1,3 diaxial interaction with the other axial groups, and that this is a steric. This involves steric strain. So the larger this group, the more steric interactions it will have. If it's just a proton, we really don't worry about it. So any large group, this would be a steric interaction because it's just like a Gauss interaction. So that's basically the source of it. It's really two Gauss interactions. Okay, so what we then need to be able to do, if we're going to follow this through to its logical conclusion, is we're going to put a number of different groups. Like with one, if you've got one group on a monosubstituted cyclohexane, the one conformation, the group will be equatorial. One conformation, the group will be axial. The most stable will be the equatorial because there's no 1,3 diaxial interactions. But once we have two groups on a ring, then we have to be able to draw the two conformations and see which of the two is the most stable. So in this case here, this first one, and what we actually also need to be able to do is translate a two-dimensional drawing like we've got here into a three-dimensional chair conformation. And so this is loads of fun. Yes, so what's the best way to do this? Okay, so yeah, let's do this. I'm just going to draw another version of the same molecule here. Okay, so when we've got a diagram like this, what we're saying is that we're squishing flat the ring. So the ring is flat, we're squishing it flat mentally, and it's in the plane of the blackboard. Anything with a wedge line, like the methyl groups pointing towards us, that means it's coming up. It is, so a wedge would be something, because we're looking down on this molecule, this wedge would be up. And anything which was a dashed line going away, which would be a proton here, because it's a dashed line, this would be down. So if we want to convert something where we're looking from above down on a molecule to something where it's a sideways perspective like this, what we need to be able to do is figure out which group is pointing up on any given carbon and which group is pointing down. And what we're going to see is that axial doesn't necessarily mean up, and it doesn't necessarily mean down, and neither does equatorial, because sometimes an equatorial group will be pointing up, sometimes an axial group will be pointing up. So here we've got two adjacent carbons, 1, 2, that have substituents on them. So typically, if I'm going to convert a two-dimensional structure into a three-dimensional structure, the first thing I always do is label my carbons. And for whatever reason, I always choose this carbon here as number 1. Because this carbon, which I've labeled number 1, this carbon here and this carbon here, for me, always correspond to this carbon here and this carbon here. And it doesn't matter which chair you've drawn, it's just really useful that these two represent these two carbons, which means that in your chair conformation, these two carbons here will be the ones pointing toward, which will be closer to us, and these two carbons will be the ones further back, those two. So it's just my personal convention. You can have your own if you like, but if I label this 1 and 2, I would label this carbon here 1 and this carbon here 2. And if this is going clockwise, I always make sure that going around the ring, this ring is also clockwise. So this would be carbon 1, this would be carbon 2. 1, I guess. Then we need to put our groups on. So we've got methyl group on carbon 1, it's got a wedge. So it is pointing up. So on this carbon here, so this is a chair flip, so these will be in equilibrium. In this carbon here, there is a group which is, this is a valley down, so there's a group pointing down, straight down, which is axial, and then there's a group pointing up here, which would be equatorial, which would parallel these lines, right? And on this carbon here, after the ring flip, it's a peak, so there'd be a group pointing up, which would be axial, and then there would be a group pointing down, which would parallel these lines. And so basically what we do is then we say, okay, what group is up on carbon 1? The methyl group is up. So in this conformation here, let's erase this arrow, we would put a methyl group, because this is up, and the group which is down would be the proton. So in this conformation, this methyl is in the equatorial position. It's pointing up though. In this conformation over here, it's a peak up. The methyl group would be pointing straight up, and this H would be over here on the right, pointing down. So the H is down in each case. So you'll see in the conformation A on the left-hand side, the methyl group is equatorial, and in conformation B on the right-hand side, the methyl group is axial. Now we haven't finished our diagram because carbon 2 has also got a methyl group pointing up. So on carbon 2 on group A, this is a peak up, so there's a group pointing straight up, and that would be a methyl group. And on carbon 2 over here on B, it's a valley, there's a group pointing straight down, which would be H. And then the methyl group, this line here would be parallel to this line, which would be up. And so in each case, the methyl groups are pointing up, but there are, and in each conformation, one methyl group's equatorial, one methyl group's axial. So if I was to say to you, which of these two conformations is the most stable, and the only sort of steric interaction that we need to worry about for these is 1,3 diaxial interactions. Is one of these two conformations more stable than the other, or are they equal in energy? So what one thing you can do is just total up the number of axial groups you've got, and if one has got more, then that one would be the least stable. But in this case, we've got, let me see if I can change my color here, red, okay. Conformation A, we've got methyl group, which is axial. Conformation B, we've got a methyl group, which is axial. So, and the other ones are equatorial. So this would be, these are basically equally stable. So it would just be an equilibrium. between the two of them now, but this isn't the case all of the time. So in 1,2-dimethyl cyclohexane, cis dimethyl cyclohexane, one conformation is clearly more, they're both, the same. What we're going to do is we are going to try the same thing with the the trans version. And what we're going to see there is that the two of them will be will have different stabilities. Just erase all this stuff. Stop. Right, so this little part here is basically how to convert these two structures together. So it's basically following what I tried to show before, that being that I like to label this 1 and this 2, and this is going to be clockwise, 1, 2. So we've already drawn our chairs. Then we look at this carbon and determine which one's pointing up and which one's down, and if we need our methyl group. Right, yes, I will do that. So I'll get to that in a second. So we're basically on each carbon, we're doing an analysis to see which group is pointing up and which one's down, and then adding the substituent in the appropriate fashion. So the methyl group was up on this carbon, the up group is equatorial. On carbon 2, the up group is axial. And so when we undergo this chair flip, carbon 2, the axial group becomes equatorial. Carbon 1, the equatorial group becomes axial. But you'll notice that in each case, these methyl groups are still pointing up. They never go from pointing up to pointing down. They're always pointing up. So this conformational change doesn't change the direction of if it's pointing up versus pointing down. It only changes if it's in an axial position versus an equatorial position. And those two interconvert. Now, when it comes to energies, which of the two chairs is more stable? So to be more stable, so lower in energy, we need to minimize the number of 1,3 diaxial interactions. So on the conformer on the left, this methyl group has got 1, 2 diaxial interactions. And on the conformer on the right, this methyl group has got 1, 2 diaxial interactions. So both of these are equally stable because each one has got one group which is axial. What we're going to see later on is that this isn't always the case. Sometimes one conformation has got 0 1,3 axial interactions, and the other conformer could have multiple. So we're basically, the general rule of thumb is you look at your group and you determine how many diaxial interactions you've got, or your conformation, how many 1,3 diaxial interactions you have. The more stable conformer will have the fewest number of these interactions. So that's basically how this is going to work. So for this molecule, the cis 1,2-dimethyl cyclohexane, they're equal. So the two conformations are completely equal. Now the trans 1,2-dimethyl cyclohexane, this is not the case. So if we do a similar sort of analysis as what we did before. So we've got our two chairs, and let's look at this with the laser here. So the chair on the left, this carbon is pointing up. The chair on the right, the same carbon's pointing down. So your two chairs, the 2 points, like in this case, they're pointing towards one another. So you can always tell if you've drawn the correct two chairs, like this point points here, this point points here. So these are in fact the two different chairs. So another way of drawing this would have been like this. So this is pointing towards there. So doesn't matter if you've got this chair on the left or this chair on the left, as long as the two of them sort of, the little pointy parts are pointing towards one another, you know you've drawn the two chairs. And we need to be able to draw both chairs. Sometimes people can draw one chair really well and one chair not so well. For this type of analysis, we need to be able to draw both types of chairs. So I've labeled my favorite carbon, carbon 1, and then carbon 2, and this is clockwise. And so this is, if you're looking down, this is clockwise as well. So if you're looking down, this would be a clockwise. Carbon 1, carbon 2. Carbon 1, the methyl group is pointing up because it's got a wedge. So on this carbon here, the group that is pointing up is equatorial, and on carbon 1 on this carbon, the group which is pointing up is axial. So in both cases, these two methyl groups are pointing up. On carbon 2, this is a dashed line, so this means that this is down. So on carbon 2 here, this is a peak, and the group which is pointing up is a proton. So the group which is pointing down has to be the methyl group, and it's equatorial. In the conformation on the right-hand side, this is a valley, and the group pointing straight down is the methyl group down. So both of these conformers are consistent with the two-dimensional drawing. Carbon 1, methyl group up, carbon 2, methyl group down. Carbon 1, methyl group up, carbon 2, methyl group down. Carbon 1, methyl group up, carbon 2, methyl group down. And if we were to do a similar analysis as to which one is more stable, you will notice that, you erase this. If we draw here some protons, this methyl group here has got these diaxial interactions with those two protons. And this methyl group here has got diaxial interactions with those two protons. So this conformer on the right-hand side has got two sets of 1, 2, 1, 3 diaxial interactions. This group on this conformer on the right has got none because both of our methyl groups are equatorial. So there's 0. And over here, there's two sets of 1, 2. So this one is going to, the chair on the right is going to be far more less stable because of these interactions, which is probably exactly what I put on the next slide. I better erase all this mess. And so if we had this as a sort of exercise, this equilibrium, we could say with a great deal of confidence, this chair conformation would be the more stable than this one because there's no 1, 3 diaxial interactions. And so if you take a bottle of this, 99.9% of these would exist in this form as opposed to this form. And so, yeah, that's basically the next part of this class is being able to draw both chair conformations and translating those two-dimensional structures something like this into a chair and then doing an analysis and determining which of the two chair conformations is the most stable. So that's basically where we're going with this next class. So we need to be able to draw chairs. And so that's basically why we had a little breakout session and practice drawing them. So that's what we're going to do next class, is get some practice translating two-dimensional structures into chairs and then determining which one is the most stable. Were there any questions at all? Since I didn't actually ask, a whole lot. Let's see here.
I mean, it's not really a question, but are there any interactions with the equatorial groups ever? Because we talked about diaxial interactions. Is there any
right. So it turns out that if the two groups, that's a good question. If the two groups are on carbons right beside one another, let's see here. This methyl group and this methyl group are on adjacent carbons. And if they actually do have a Gauss interaction like this, but there's only one. So that would be 1/2 of the energy associated with this methyl group interacting with the proton here and the proton here. So
sorry, so one Gauss interaction is equivalent to one diaxial interaction?
One Gauss, a 1,3 diaxial interaction is actually 2 Gauss because there's 2 of them.
Yes. So,
right. So
it's roughly equivalent for.
You would need
another group for it to be truly equivalent here.
Yeah, you would need 2 of these sort of Gauss interactions here to equal one of the 1,3 diaxial. So usually for that, and you only have these Gauss interactions if the 2 substituents are on carbons that are right beside one another. So so you can basically get away with, so often we don't bother even counting them because it's only 1/2 of a 1,3 diaxial interaction and they have to be adjacent. So if you've got 3 substituents that are not adjacent to one another, there's zero steric interactions with that.
Okay.
I had a question about the nomenclature. If there isn't a nomenclature part in your textbook, what resource to use? So
I used Crash Course.
Crash Course?
Yeah.
I think Khan Academy has a little thing on how to name things. It's basically it's the way you start is by if it's a hexane and like an alkane, you basically try to number the longest possible chain, which will give you your base is it a hexane, is it a pentane, is it a octane, that type of stuff. And then if you've got substituents on it, you want them to have the lowest number. So in this case, I could have numbered this the direction I did, or in the opposite direction, 1, 2, 3, 4, 5, 6. But if I number it the way I did with the pink, 3 is less than 4. So this would be, and this is a methyl group. So this would be 3-methyl hexane. Yeah, I think like if you don't have a textbook which talks about this, one of the basic ones, like the Khan Academy's got that. And what was the one you said you used? Crash Course?
Yeah, I used Crash Course. They have an organic chemistry video playlist.
Okay. I will probably have 1 or 2 nomenclature questions on the next assignment. They won't be particularly difficult. Later on in life, if you become an organic chemist, there's going to be a computer program which you can just throw your structure in and it will name it for you. So it's one of those, it's one of those holdovers I had from my undergrad, which I loathe and despise. So I try not to torment everybody with it. So, but if you have any questions on it, if you've got a question, just send me an email and I'll help answer it. I have no problem doing that. Okay, so what we'll do next class is we'll do some chairs, converting two-dimensional chairs into two-dimensional drawings into chairs, doing an analysis of it, and we'll probably be able to start the section on stereochemistry, which is again another sort of visual sort of thing. So we'll do that next. All right. Were there any other questions? All right. Well, have a good day, everybody.